Hi everyone, this is the video for section 6.4, which is titled Nth Roots. You might have some experience with working with roots from Algebra 1 class, so we're going to kind of see what you have for base knowledge and then expand on it from there. So we're going to be looking at taking what we call the nth root, which means it could be square root, it could be cube root, it could be fifth root. So the variable n is going to represent what root we're taking. And like I said, in the past, you've probably worked with square and cube roots the most, but we're going to extend that a little bit more in this course and look at roots like fourth roots and fifth roots. So before we really get into problems, the first thing I have to make sure that you understand is a little bit of the symbolic representation in the vocabulary that you're going to see as you work. This example right here is read the nth root of 81. The value of n is called the index. You might hear me or other people also refer to it as the root. The number or the value underneath the radical sign is called the radicand. And that symbol that I just named here is called the radical sign. So you should be familiar with that terminology. I'll use it in class. I'll use it on videos. I'll expect you to be able to use it as you speak about problems and the topics during class time. So pretty simple right there, just the representation in the vocabulary. Make sure that you understand what each piece is. And we'll move fairly quickly in this section into some situations and then some examples. So based on what I just said about the index, we basically can have two types of indices, either an even index or an odd index. So I'm going to give you some scenarios, really the only scenarios you can have for both situations. The first is if we have an even index and a radicand that's greater than 0. Now an even index would be something like a square root or a fourth root or a sixth root, something like that. And a radicand that's greater than 0 might be something like 25. It could be 13, as long as it's positive. I use 25 because it's a perfect square, and I'm using a square root here to kind of illustrate the idea. Anytime you have this scenario, even index and a radicand greater than 0, we end up with both a positive and a negative real root. Now, if you're solving an equation, usually, or you have to include both of them. We will, for the most part, unless specified otherwise, include what's called the principal root for these. So the positive answer is called the principal root. So you'll get used to hearing me say that, and we'll talk a little bit more in class about the meaning of the principal root. If we have an even index and our radicand is less than 0, meaning we might have this scenario, the square root of negative 25. That leaves us with two answers, two roots that are positive and negative, and they're complex because we have to bring the i's into our answers. So we'll have a positive complex root and we'll have a negative complex root. So in a problem like this, we would end up with positive or negative 5i. The one before, we would have positive or negative 5 as our final answer. The next scenario and the last scenario for an even root would be, or an even index rather, would be to have an even index and a radicand of 0. So that would be something like the square root of 0. And the square root of 0 is equal to 0. We automatically get 0 whenever that radicand is equal to 0. So those are the three scenarios for even index type problems. If we have an odd index, so that means we might have something like a cube root or a fifth root or a seventh root, and our radicand is greater than 0. For example, I'll use 8. The cube root of 8 turns out to be 2, because 2 times 2 times 2 gives us 8. So every single time we have an odd index with a positive radicand, we get one positive real root. If we have an odd index and our radicand is less than 0, for example, the cube root of -8, that will yield -2 as an answer. We end up with one negative real root. And finally, if we have an odd index and our radicand equals 0, it's the same as the even index situation. We end up with 0. So it's good to wrap your mind around the different types of scenarios. It's not that you have to memorize this. It's just that it should be something that makes sense to you as you go through and you do your work. It'll give you something to think about if you're headed in the right direction with your answers. So make sure you get these in your notes, and I will take questions on any of the terminology or any of the scenarios that I covered there. So we're going to try some examples next. The first is going to be to find the positive and negative root of the square root of 16y to the 4th. The directions for the most part will say simplify on these. Now in this problem you see in front of it positive and negative. That means you definitely have to provide me with both roots. If you do not see that positive or negative, if there's nothing there, then you can give me just the principal root if you have an even index. So this is the same as the square root of 16 times the square root of y to the 4th. We can break our factors apart in a multiplication situation when we have that in a radicand. The square root of 16 we know is 4. And the square root of y to the 4th, I don't know how much experience you have with doing something with variable bases, but we know that the index for a square root is 2. So we take our index and we divide it into the power that we're working with. So 2 goes into 4 2 even times. That means I can pull y squared out of the radical. And because there's no remainder, there's nothing left that stays under the radical. So my final answer for this, I have to include the positive and negative sign, would be positive and negative 4y squared. I can double check my work by squaring those answers, and I should get the radicand back. If I square 4y squared, I get 16y to the 4th. If I square negative 4y squared, I also get 16y to the 4th. The second problem is another even root problem. So remember, if there's nothing written, it's assumed to be a square root. There's an imaginary index of 2. So this is saying that I want the negative square root of the quantity of x squared minus 6 to the 8th power. Now this radicand is quantified underneath. So I'm going to treat this as one entity here. So it's basically like I'm taking the square root of something to the 8th power. Now the square root of something to the 8th power, 2 goes into 8 4 full times with no remainder. So that means I can pull out the radicand with a power of 4 on it. No remainder, so nothing stays underneath, and this is my final answer. The opposite of the square root of the quantity of x squared minus 6 to the 8th is equal to the opposite of the quantity of x squared minus 6 to the 4th. In part C, we're asked to take a 5th root. So I can break things in pieces again. This becomes the same as the 5th root of 243 times the 5th root of a to the 20th times the 5th root of b to the 25th. I don't expect you guys to be breaking this up all the time, maybe at the beginning so that you get an idea of what to do, but you guys should be able to look at this eventually and just do it all right from the original example. The 5th root of 243, we have to think to ourselves, is there a number that can get multiplied by itself 5 times to get us to 243? So I know that 2 to the 5th is 32, so I'm a little bit low there. But 3 to the 5th will be 3 times 3, which is 9, times 3, which is 27, times 3, which is 81, times 3, which is 243. So I get 3 from this one. The 5th root of a to the 20th is a to the 4th. 5 goes into 24 whole times, no remainder. And the 5th root of b to the 25th is b to the 5th. 5 goes into 25, 5 whole times, no remainder. So my final answer is 3a to the 4th, b to the 5th. The last one on this screen is the square root of negative 16 x to the 4th, y to the 8th. I'm going to try to do this one without breaking it into its pieces and see how we do. We know that if we're taking the square root of a negative value, our answer is going to involve i's. And the square root of negative 16 is 4i. The square root of x to the 4th is x squared, and the square root of y to the 8th is y to the 4th. So the principal root, I don't have the positive and negative in the front there. The principal root of this is 4i x squared y to the 4th. If you wrote down positive or negative 4i x squared y to the 4th, I'm not going to mark you wrong. But if nothing is written there, then just giving me the principal root is sufficient enough. So let me know with these 4 if there are any questions when you come in. I'm sure there will be some, and we can discuss. There's one more in this little set of problems I want to make sure that you get. This last one is the 6th root of 64 times this quantity of x squared minus 3 to the 18th. So when I look at the radicand, I see 2 pieces being multiplied. I see the 64 and I see the x squared minus 3 to the 18th. So I'm going to look at taking the 6th root of each of those values. The 6th root of 64 is 2. And you guys might be a little shaky with some of the roots, and it'll take you a little bit of time to get used to it. We can go through some methods that you can use in class to kind of make yourself more efficient. So the 6th root of 64 is equal to 2. The 6th root of something to the 18th power is going to be that something, the x squared minus 3 to the 3rd power. So the final answer here is 2 times the quantity of x squared minus 3 cubed. Again, the principal root is sufficient because we don't have the plus or minus in front of anything. So we'll talk a little bit more, like I said, about these types, and we'll see how you do when you get into class with things. I'm going to do just a little bit of the next section because I think you're ready for it. I won't overwhelm you with the entire section, but I do want to talk about a few of the operations that we're going to work with radical expressions. Mainly in this video, the product and quotient properties, and I will do sums and differences with you in another video. So in this section, the entire section, ultimately you're going to be able to use the 4 operations with radicals: add, subtract, multiply, and divide. And for this video, like I said, we're going to focus on the idea of multiplication and division. Multiplication in the sense, this product property, not really multiplying too many things together. And then we'll bring it back more as a whole towards the end of the section. The first, there's a few properties in here. The first property that you need to know is called the product property of radicals. And this product property of radicals says that if we have the nth root of a times b, so this could be any root, it could be an even or an odd root, of 2 values which are factors, a times b, then what we're allowed to do, and you saw me do this earlier, that's why I think you're ready to cover the material here, turns into the nth root of a times the nth root of b. You saw me breaking things up a little bit earlier. Now this holds true as long as if n is even, so if our index is even, then a and b have to be non-negative. The values underneath have to be non-negative. And if n is odd, it doesn't matter what we have underneath in order to get a real number answer. So we're talking about the real number system there. Make sure that property is in your notebook. You'll see how it's going to be applied here in a second with a couple different problems. For the most part, you've got to understand the idea with the problem. Sometimes these properties can get a little wordy and they're a little bit complex to understand. So these are going to look very similar to the problems that we just did. The square root of 32x to the 8th. Simplify this. Now, taking the product property really into account says that, and this is what I said I kind of wanted you to get away from doing, takes us into the square root of 32 times the square root of x to the 8th. Just realize that if it makes life easier, you're allowed to break things up like this. You do not have to. I really don't expect you to at your level. So doing it in one set, like from the original, would be the best. Now, the square root of 32, what's going to happen in this section is we may not have perfect squares. So we've got to think about what value falls within 32 that is a perfect square, and we really want to think about the largest. So 32, 32 is 1 times 32, that's not going to work. 2 times 16. Now 16 is a perfect square, so we can break 32 up into the square root of 16 times the square root of 2. And I know that the square root of x to the 8th is going to turn out to be x to the 4th because I'm going to take the index of 2 and divide it in. I'm not done over here yet because I need to simplify further. The square root of 16 is 4. That came out of the radical sign. The x to the 4th is out of the radical sign. And I'm going to keep the 2 under the radical because that can't be simplified. I can't take the square root of that. So my final answer is 4x to the 4th radical 2. Now, some of you, if you have trouble trying to find a perfect square within the value that's in the radicand, if I take 32 and I do the prime factorization, so I start with 2 as my smallest prime number, divides in 16 times. I can either look at what I have and see if I have any perfect squares within my work, or if I don't recognize, I can keep doing the prime factorization all the way down and then start to group pairs of like factors. So here's a pair of 2's and here's a pair of 2's. That means that 16 is a perfect square. 2 times 2 times 2 times 2 is a perfect square within 32. And it means that I'm going to have 4 come out of it because there are 2 pairs of the 2's. And that's where that 4 can come from. So that's kind of a tedious approach if you get stuck with a large number. I think as you get more into this and you get used to it, you're going to be able to do it without having to do the prime factorization chart. So the next one is the 4th root of 16, a to the 24th, b to the 13th. This is one I think we can do right off the bat. The 4th root of 16, we should recognize as 2. The 4th root of a to the 24th is a to the 12th. And the 4th root of b to the 13th, now this is the first time that we've seen something that doesn't divide in evenly. I'm going to take the 4 and divide it into the 13. That goes in 3 whole times, so I'm going to pull out a b to the 3rd. And I have 1 power left over to get to the 13. That's going to stay underneath the radical sign because I can't simplify that any further. So my final answer is 2a to the 12th, b to the 3rd times the 4th root of b. Again, we'll work with this. The point is to practice this in class. So we can talk about questions first, and then as you work, I can try to help point out some issues that people may be having. I'm just going to erase this because I needed to pull the screen up. So the last property that we're going to talk about today is called the quotient property of radicals. Quotient meaning division. And this property says that if you have the nth root of basically a fraction, a over b, and this can be any root as long as the index is greater than 1. We can't have a negative index. What you're allowed to do is to split up the numerator and denominator and kind of work it as 2 separate problems. So this can become the nth root of a over the nth root of b. And I want you to keep in mind that these properties, because there is an equal sign between them, they kind of go both ways. So if I was presented with a problem like this, I could turn it into that scenario as well. Again, we want to make sure that the index is greater than 1, and a and b have to both be real numbers. B can't ever be 0. And why can't b be 0? If you think about that for a second, hopefully you're going to tell me that if b were to be equal to 0, that would make the denominator of a fraction equal to 0, and that can't happen. We have a situation then that would be undefined. So that's why we have to put that qualifier on whatever that denominator is. So those are the technical terms of the quotient property of radicals. We'll jump over to the next screen because there's one other rule that I have to introduce to you or reintroduce, whether you may have seen this in Algebra 1 before, is that when you work with a quotient, there's one rule that one situation you must never leave, and that is you can never leave a radical in the denominator in your final answer. So we have to do what's called rationalize the denominator. And that when we rationalize the denominator, we're going through a process in order to get the radical out of the denominator. We can't keep it there. So I'm going to go through 3 different problems with you, 3 different scenarios that you might run into. The first is 3 over the square root of 2. Now, the problem here is the square root of 2 in the denominator. I can't simplify either of these. I can't do anything with the square root of 2, so it's not like I can reduce that to anything or turn it into some other form. So I'm stuck in this situation, but I know that I can't have the square root of 2 in the denominator. So I have to ask myself, how do I undo a square root? And as I think about that, I remember that if I square a square root, the radical disappears. So what I'm going to do is multiply the denominator by the square root of 2. So I keep the exact same radicand, and when I multiply a square root by itself, we know that the radical will disappear. Well, if I only multiply it in the denominator, I'm going to change the entire meaning of the problem. So we know in math that in order to not change the meaning of a problem through multiplication, we have to multiply by an equivalent of 1. So what I do to the denominator, I also have to do to the numerator. So this is going to change the look of it, but because I'm technically multiplying by 1, I'm not going to change the meaning of it. My new problem is going to look like this. 3 radical 2, I can't do anything with those because one number is outside the radical, one is under. But the square root of 2 times the square root of 2 just turns into 2. So I've just done what's called rationalize the denominator. I've gotten the radical out of the denominator and put it in a more presentable form. And that's the process that we're going to have to go through. It's really easy with square roots. It gets a little bit harder when we work with other indices. So the next one I have is 5 over the cube root of 2. Now we have to figure out what to multiply this by. Now to undo a cube root, we have to multiply something by itself 3 times. We have to cube it basically. I have right now a power 2 to the first power underneath that radical. I need, in order to get the 2 out of the cube root, I need a power of 3 on the 2. So that means that I need 2 more powers of the base of 2. This will give me a power of 1 here and 2 more powers here, which will give me the cube root of 2 cubed, because remember when I multiply like bases, I add my powers. And when I take the cube root of 2 cubed, when my power matches my index, I'm able to take the radicand right out of the root. So I'm going to have to do this up in the numerator as well. Now I left it as 2 squared. I know that 2 squared is 4. When I write my final answer, I'm going to simplify that in the numerator. This is going to become 5 times the cube root of 4 over, this is just going to leave me with what was under the radicand originally, or just 2. Because this technically turns into the cube root of 8, and the cube root of 8 is 2. So my final answer is 5 times the cube root of 4 over 2. The last one here, I kind of threw a twist into things. We have the cube root of 9a. So I threw a variable in there, and I threw another numerical part to the radicand. I know I need to undo the cube root, so I need a cube root of something to some power. Now 9 is technically 3 squared. So I have 2 powers of 3 already. I need 1 more power of 3 to match the index, and I need 2 more powers of a to match the index. So that's going to leave me with multiplying by the cube root of 3a squared over the cube root of 3a squared, which will yield an answer of 4 times the cube root of 3a squared over, now this is going to turn into the cube root of 27a cubed. The cube root of 27a cubed is 3a. Final answer. I know there are going to be questions on this, so I expect you guys to ask about what you don't understand, and we'll definitely do some more practice problems in class together. So one more little set here before we're done. And these 3 problems are the following. We're simplifying again, but they all involve a quotient. And the first one is the square root of x to the 6th over y to the 7th. Now, I'm going to look at this as splitting it into using that quotient property of the square root of x to the 6th over the square root of y to the 7th. You don't have to write this like this all the time, but I want to get your mind thinking it. The square root of x to the 6th, remember our index is a 2, turns out to be x cubed. The square root of y to the 7th, if our index is 2, turns out to be y cubed with 1 y left under the radical because of the remainder. So the problem here is that we have a radical left in the denominator. It's a square root, so I multiply by the square root of y to undo it. And that means I have to multiply the numerator by the same thing to keep that equivalent of 1. And my final answer will turn out to be x cubed radical y over this right here, radical y times radical y is y, times y cubed is y to the 4th. final answer. I may be completely confusing some of you guys, or you may have trouble following this, but again, this is when you need to make sure that you ask questions in class when you come in. Part B is the fourth root of 6 over 5x. Again, this is the same as the fourth root of 6 over the fourth root of 5x. So sometimes it's helpful to actually see it split. Sometimes it's harder to look at it when it's one fraction underneath the radical sign. Now, I can't take the fourth root of 6, so I'm going to leave it as the fourth root of 6. The fourth root of 5x. Now, that's a radical that I can't simplify, but I need to rationalize. So right now I have 1 power of 5 and 1 power of x, and I'm taking the fourth root. I need to total the power to equal the root. So I'm going to need to multiply by the fourth root of 5 cubed. I need 3 more powers to make 5 to the fourth, and I need 3 more powers of x also to make x to the fourth. So this is going to become, what did I do? I think I messed you up. I was rationalizing here. So I need to rationalize by the fourth root of 5 cubed x cubed, and I need to do that to the numerator as well. I was one step ahead of myself in the numerator. So this is going to leave me with the fourth root of 5 cubed is 125. That's got to get multiplied by the 6 that's there. So I believe that's 750 x cubed over, this is going to turn out to be the fourth root of 5 to the fourth, x to the fourth, and that will leave me with 5x in the denominator. I always want to check to make sure I can't simplify the number that I end up with under any of the radicals, and there is no perfect fourth root in 750, so I'm going to leave my answer exactly as is. It does get a little complicated with some of these problems. Now the last one here is the square root of 27/3. Now according to what we've been doing, the rule says that we're allowed to break this up into the square root of 27 over the square root of 3. I'm going to look at the numerator. The square root of 27 is the same as the square root of 9 times the square root of 3, so we're involving the product property there, over the square root of 3, which I notice this. I can reduce those out, and I'm left with the square root of 9, which is 3. Now, that's one option. Remember what I said a little bit earlier. We can take this, and we can look at that as a whole. The square root of 27/3 is really 27 divided by 3 is 9, so this turns into the square root of 9, which is 3. So if you recognize that you can simplify the fraction before you begin taking the root, life may become easier for you, and in this case, it's much more efficient than going through the process of splitting it up into the 2 separate situations. So those are the types that you're going to see with some of the problems in class. Like I said, I'm going to help you. I'm going to answer questions. We can work together on them so that we get any confusions taken care of. The last thing I need you to get in your notes is this. A radical expression is in simplified form when the following conditions are met, and we're going to talk further about this in class. The first is that the index is as small as possible. So the root value is as small as possible. The radicand contains no factors other than 1 that are nth powers of an integer or polynomial, and we'll talk about what that means. The radicand contains no fractions, and then finally, no radicals appear in the denominator. So when those 4 conditions are met, we have a radical expression that's considered to be in simplified form. It's not as complicated as it sounds, and we'll talk about each of these bullets in class together as we go through and we work with some of the problems about whether something is considered to be simplified or not. So that's all I have for section 6.4 and part of 6.5. Make sure that, if you do have any questions, maybe they can be answered by rewinding and going through things again. But if not, highlight what you need to in your notes and be prepared to talk about it when you come into class next time. Thank you for listening, and I will see you in class.